the 90s to the mathematics of the 21st century and deal with n equals 2 mathematics, two-dimensional mathematics. In this process, well, hopefully you would notice the transition. I hope it would be pretty smooth. But in the process, of course, there might be some inconsistencies, and I ask you to bear with me. I also had a terrible nightmare last night. Well, actually, somehow it was related to the evening lectures. You know, it was really terrible. First, I was called on by the ghosts of Faddeev and Popov. Faddeev and Popov. And but the worst came later, and that was, I really freaked out. Later, it was Turaev's shadow, supported by Holler Shetikhin. So I guess I need after this conference, I will have to go through some kind of renormalization process. So, graph homology. We already had a beautiful presentation by Karen Voltman last night of one version of the graph complex. I will deal with a slightly different one, which deals with so-called ribbon graphs. Some people call them flat graphs. I think there are other names. So let's consider the classes. Oops, where do I have G, M, for m greater or equal to 1. Let's consider it will be a vector space generated by isomorphism classes of pairs gamma O, where gamma is a non-empty connected graph with m vertices of valence, all of valence greater or equal to 3, and O an orientation on R, the E of gamma, plus H1 of gamma with coefficients in R. So we take this vector space generated by that E of gamma is the set of edges of the graph gamma. And if you think of a graph as a one-dimensional CW complex, then H1 of gamma is its first cohomology group with real coefficients. So we take a vector space, the vector space spanned by these graphs, by isomorphism classes of these graphs over Q, and we mod out by the relation gamma minus O equals minus gamma O. It's very similar to what we considered before last time when we looked at the associative, the A infinity operand, which was represented by the tree complex, and there are a few differences. Oh, actually, I forgot to say ribbon. That's ribbon graphs. That's very important. So the only difference is that here we allow not only trees but also graphs, and the second difference is that there trees has leaves, that is the root and the leaves. Here those graphs don't have any free legs. They're just sort of contained, very similar to those graphs. Well, actually the same. It's supposed to be the same as those graphs that Misha had in his treatment of Feynman diagrams. Well, but here we allow all possible valences starting from 3. So, for instance, the simplest graphs I can sketch would be like that. So it's based on two first. Huh?
Can you say what ribbon means?
Yeah. Okay. Ribbon means hold on. A ribbon graph means that for each vertex, it takes a cyclic order. We fix a cyclic order on the set of incident for adjacent edges. So that means locally, those graphs look like planar graphs, but not necessarily. Well, and of course, planar graphs inherit a ribbon structure from the orientation of the plane, but in principle, these graphs may not be necessarily ribbon. Just imagine sketching a graph of this type on an oriented surface. Then you would have an example. Locally, of course, you would have an orientation. You would have a cyclic order of the edges ending at incident to this vertex, but globally, it wouldn't be. You wouldn't be able to put it on the plane necessarily in general. So, for instance, here is an example of a graph like this. This has one vertex and two edges, which are self-loops and which are tadpoles in physical terms. And the cyclic order given by this picture over here, I mean by the plane picture, but I sketched in 3D space, and this actually, you can sketch this graph on a torus, obviously, and we'll do this in a second. But before that, I want to define a differential from this complex. So this will be the mth space in the graph complex. I will define a differential d from gm to gm minus 1. And this will be an operator whose square will be equal to 0. And the formula goes like this. It's sort of, well, actually, I'm talking about graph homology today. And yesterday, I was also talking about some homology or some complex, the tree complex. But this tree complex was really, that tree complex actually was defined so that it gave cohomology rather than homology. In fact, you can consider, whatever complex you write down, you can dualize, take the dual vector space, and you will get you will pass between homology complexes producing homology and cohomology. Oh, it's here. M vertices. I'm sorry, my M tend to become a photon at the end. Yeah.
So these are supposed to be sort of the zero state graphs?
No.
No.
Not genus zero.
Meaning not decorations of private vertices.
Yes. No, this is supposed to be arbitrary genus. And we'll see in a moment how this all stuff works. So the differential is the summation over the edges E. So edges, let me say edges E, which are not equal to loops starting from edges which start and end at one and the same point. And you sum up over all these edges, and you take the contracted graphs That is, you contract this edge. Remember, last time it was the other way. You looked at all possible graphs which contract, whose contraction at one edge gives you the given graph. Now we take all possible contractions. It doesn't really matter. I just wanted to be consistent with today's talk. With what follows, namely with homology of modular spaces, and somehow I feel better doing first the homology there. Now, with induced orientation on the set of, well, obviously H1 wouldn't change, and so the induced orientation coming from, again, putting this extra edge as number first, as the edge number first, and that way passing back and forth between the two orientations on the contracted graph and the original graph, and obviously using this fact that the first beta number of the graph didn't change. There is a natural isomorphism like this. So using this embedding and this isomorphism. Okay. So this is the differential in the graph complex. And as you can see, if you take only... Well, actually, there are many graph complexes. You may consider many graph complexes, and there are different versions. You can add legs to the graphs. You can consider graphs with legs, and you can restrict yourself to trees only, and this would be yesterday's graph complex if you also take the dual of this complex. And also, you can consider not ribbon graphs. That is, yesterday we also got planar trees. Ribbon trees are nothing but planar trees. So you can consider not necessarily ribbon graphs of planar trees, but you can consider just abstract graphs or abstract trees. And if you perform this construction for abstract trees, you would get the complex that was discussed, another graph complex, which was discussed yesterday by Karen Voltman, but she had some unbeautiful structure on it. And if you forget, for trees, if you forget the word planar, then you would be describing L-infinity algebras and the L-infinity operand. This corresponding operand of trees will be the L-infinity operand, and this is what is described in my notes, which are in some strange way being distributed here. But hopefully the first two parts were put on the desk there at the entrance in the morning, but the third part, although it exists, for some reason didn't make it through. But they promised that it will show up soon. Yeah.
You said at the beginning that you take a vector space generated by this. Is there any reason for a vector space to you work over Z?
Yeah. I think maybe for this complex I can work over Z. Actually, yesterday I took it over Z, but I think I was supposed to take it over Q then, because there every.
So the answer is yes to this question. You take it over Z. Except the n squared will still be 0.
Yeah. Yeah, I will get maybe something different. So what did I think? Oh yeah, I think that.
Sometimes you want the false zeros, so maybe you're only zeros.
Well, this basically deals with this fact that if you have on a graph, if you have something and then a simple loop that is one edge which ends and starts at the same point, then I want to have this whatever orientation is 0, and this follows from this rule, but actually it doesn't.
It's not relevant.
Yeah, it's not relevant today. So I can put it. I can put Z, but later on I will do it over Q. Or let me to avoid more notation, let me put Q here. Yeah, it doesn't matter for the differential, nothing will change. That's right. All right. Now,
So can you assume that it says sum over edges D, let's say not equal to 0? It's not
not self loops, not dead poles.
Okay.
Yeah. So some box here like that. All right. So this way we obtain a complex GM. It will be an unbounded complex. It will start somewhere. I mean, it will start nowhere, and it will go from the unknown, the uncertain, to the certain, which is G1, and then to 0. Okay. Now let me do the following construction. Why are these Riemann graphs associated to Riemann surfaces? It's a very simple idea that you can fatten each graph. And so from graphs to Riemann surfaces, well, first of all, to oriented surfaces, just with no complex structure, no conformal structure, oriented surfaces. So if you have a graph, a Riemann graph, you can fatten it. That is, you can multiply each edge by a little interval, and a little interval of the real line, and use the cyclic orders at the vertices to glue those edges, to glue those strips, those ribbons that you obtain this way, to glue them together. This will give you a unique, up to homotopy, a unique way to glue them together, cyclic order at each vertex. And this way you will obtain a certain oriented Riemann surface with boundary.
Oh, you should be careful to get an oriented surface, and you put top tweets or something.
Can I?
Well, that's oriented, basically complete.
It's oriented.
Oh, no.
It's oriented.
Put the script so that
We can merge it with
the natural version.
Yeah, I can't.
Connect them up like this. Put those things down.
Wasn't part of the definition yet.
Just put the vertices down like you've drawn, put them all down, and then just draw the roads. So draw the graph.
Well, you should mention the part of otherwise Möbius strip would be just as good as an
What
alpha.
he said.
No, Möbius strip would not go through. I mean, it's, how do you make it?
And multiply it by 10.
Yeah.
The question is, how do you glue them at this point? Okay, but it does matter. It's all good.
Okay.
Put these down and then you just connect them up.
Oh yeah, using the immersion on the plane. You can't embed it into the plane, but okay. Yeah.
Is that the only way for you? Let that be constructed. That goes up. That goes in the river graph. Give you an orientation.
Each edge you make it so that you've got an orientation on each vertex. You make each edge so that as you go along you preserve that orientation.
Right.
And then the embedding, you can put in some extra twist. So the immersion version means that the
Okay, well, maybe I should have talked about, from the very beginning, about the vector graphs. Then this would make it easier. Okay. All right. Well, if Dennis says done, it's done. So, well, for instance, for this kind of graph, you make it thick, sort of multiplied by a little thing here.
This graph is not set.
And then you also have this other graph coming out of this picture, and you make this kind of identification. So this gives you a torus with with one hole. So you can visualize this picture if you fathom this graph. That was this graph which I had earlier. You would have a torus with two holes, with one hole, torus with one boundary component. And so this is the way to see how those graphs are related to Riemann surfaces, to oriented surfaces at this moment. Now, let's consider, well, actually, this identification, this visualization of a Riemann surface out of a graph gives a decomposition of the graph complex into a lot of components. Namely, you can decompose them according to the genus of the surface you obtained and according to the number of boundary components. So, well, let's have, so G, this complex G dot, now, this complex G dot, now becomes so this is a graph complex. Its homology will be called the graph homology. The graph homology. But it actually splits into a lot of components according to the genus of the obtained curve. So you get a Riemann surface, an oriented surface of genus G for some G with n holes or boundary components. So the graph complex will be a direct sum, actually, of complexes. So these graphs now take only those graphs which, for which this process creates a Riemann surface, an oriented surface of genus G with n holes. Obviously, in the graph complex, the genus of the surface and the number of boundary components would not change. So each of these is a complex on its own. And so these are legal graph complexes we can talk about. Well, those complexes are in fact bounded. So the statement is that they will be bounded starting from the number which I computed just a few minutes before the lecture. 2n plus 4g minus 4 will be the number. Remember that these are, here I put the number of vertices instead of this dot, and the vertices of the graph complex. And so we are, the statement is that it will go from this dimension to G, and 1. Now, how to see what's going on? The point is that here you would be getting, well, the point is that this contraction of edges makes loops, makes smaller and smaller valences at the vertices. And so here you would be getting graphs which have only trivalent vertices, ribbon graphs with trivalent vertices. And say if I compute, for instance, the Euler characteristic of this graph, the Euler characteristic will stay the same because the genus and the number of boundary components is the same. So the Euler characteristic is preserved by the differential. Now let me compute the Euler characteristic. I compute it first of all as 2 minus 2g minus n from the Riemann surface that we obtained. And then, so these are, I'm removing endpoints from the compact Riemann surface of genus G, whose Euler characteristic is 2 minus 2g. And then, on the other hand, from the graph, it should be equal to the number of vertices of the graph minus the number of edges of the graph. And now, if all of the edges, so if the graph is trivalent, if all vertices have valence 3, then the number of 3 times the number of vertices will be equal to 2 times the number of edges. Right? And therefore, in this computation, E equals 3/4 of the V of gamma, and I can write down this as V of gamma over 2. So this is the number of vertices, and obviously it will be twice this number for a given Euler characteristic. So therefore, for a given Euler characteristic, this process will end somewhere. So each of these complexes is bounded and actually has finite dimension. So this is a very nice, presumably simply described algebraic complex. Okay. Now, I want to construct really a Riemann surface, not just an oriented surface, but a Riemann surface out of a graph based using some additional information on this graph, out of a ribbon graph. So suppose I have a ribbon graph which is metrized, which means that that each edge has so now consider RGN. Let's introduce the set of this is the same letter. Is it? Oh no, that's a different letter. I used G's there. Okay. Let's introduce RGN as the set of metrized. That is, each edge is given a length L of E, which is a positive real number. Everything else will be the same. We'll consider the set of metrized ribbon graphs the set of actually isomorphism classes. Well, in this context, I should say as isometry classes. isomorphism, let's preserve length. So of ribbon graphs which are connected and produce an oriented surface of genus G with n punctures. With n, not punctures, n boundary components. All right. Well, I guess I need also to condition that that the Euler characteristic of the corresponding surface must be negative. That is, the Euler characteristic must be equal to 2 minus 2g minus n, and this should be negative. So we'll consider the stability condition. Well, actually, there are so many names for those graphs. Ribbon graphs, fat graphs, what else? I think there was some other name. Does anyone remember? Thick graphs? Right, yeah. Even used at this conference. Huh?
Was it C or D? I didn't hear what you said.
Thick.
Ah, thick, okay.
No thick graphs, yeah. Maybe some band graphs, no? Twisted. I don't know, but I think with metric, they don't have a name yet, and I suggest to call them European graphs, because they have, because they're. Yeah, so to avoid confusion, let's call them European graphs, because they're on the metric system. They wouldn't know what the heck a ribbon graph is. Okay, so there are two theorems in this business of European graphs.
I think they were first introduced in a paper in 1973. Just to find
In which paper? Chekhov?
Just to find the diagrams of SU and J theory that end up with pretty relative concepts that are in that. This is the paper for He says all of this string theory is really just evolving to this idea of concepts.
Well, I know
1973 paper.
I know Bob Benner used them for.
They were used to
Yeah, definitely later, but yeah, sure. Okay, so let's take this set of isometric classes of metrized ribbon graphs, and let's construct now a compact Riemann surface out of this graph. Okay.
What happened to orientation?
Hmm?
The orientation of the mark. There was an orientation component. There was a gamma comma O in the beginning.
Yeah, always there's still an O.
Well, actually, in this case, I wonder where I put this, and if I put this. In this case, we need to consider, in fact, a little bit more. We have to consider ribbon graphs. We have to give a little bit more, a little bit finer orientation than it was introduced before. Namely, we'll consider these graphs also provided with orientations or directions, with directions on the edges. So therefore, you can think of this as putting little arrows on each edge. And we wouldn't identify if the total orientation on the set of edges that you obtain from this is the same. We wouldn't still identify if they differ on each particular edge. So we'll consider graphs like this. Okay, now here's the construction of I will introduce the construction of a Riemann surface out of a graph. So if gamma is a graph from here, we will construct C of gamma, well, gamma with a metric now, metric M. We will construct a complex Riemann surface out of this graph. So surface with punctures, with n punctures. So it will be x1. C gamma m. So it will be a surface with punctures x1 to xn. All right, how will we do this? Let's consider the following. Let's think of the following construction. First of all, I need to talk about the set of all possible orientations. So all possible directions. I call them directions. All possible directions on a graph, on the graph gamma. Then on this set of all possible directions, that is ways of pointing arrows, it will be the set, obviously, of cardinality 2 to the number of edges of the set. So on this set, I will define two operators. The first one will be sigma 1, and this will be an involution. Sigma 1 squared will be the identity. It will do the following. It will invert all orientations. So it will, for each arrow, sigma 1 will change it to this arrow. So because this is kind of picture, it will do that. Now, the orbits of this orientation are obviously the edges. You can identify the set of orbits of this orbits of sigma 1 of this involution with the set of edges of the graph. Now the second operator I want to consider will be denoted by sigma naught. And this is another operator here on the set of all possible orientations. And this sigma naught will take will do the following. It will for a vertex, for an edge, it will also be on the set of edges together with orientation. For an edge, you look at the starting point of this edge, at the initial point of this edge, and you go along the cyclic order prescribed at this vertex, look at the next edge, and take this edge with the orientation emanating from the same vertex. So it's if this edge was sigma, this edge is what we call sigma naught E. Now notice the following, that if we consider the operator sigma 1, sigma naught, and look at the orbits of this operator, you take, for each edge, you look at its initial point. And then you go to the next edge in the cyclic order at this point, and take it with the direction coming out of the same edge. So this will be...
Are you pulling back your image from the second back to the first edge?
orientation here means just, it's not orientation, it's direction. It's the same, of course, as orientation, but then you have two choices. But it's direction. So this is a directed edge. So you have another edge, which is the next, it's oriented somehow, but it's the next in this order. Say it was originally going like that. Maybe I should, maybe I should do it with this red chop. So suppose the picture was like this. We had two edges, and this is the next one in the in the order, in the cyclic order. Now we take the beginning of the edge E and take this white edge to be the image. It doesn't depend on the arrow on this edge. Now, of course, this edge gets moved somewhere else. You take this edge, and its image will be to take the initial point and take the next edge here and construct this arrow this way. So this is. Let me use sigma naught E. So that was the. Yes. Yeah. No, you also take the direction. It's not just it's not on the set of directed edges. It's on the set of all possible choices of directions on the edges. So if you have an edge which is directed like this, then you would move it to the white guy over here. If you have an edge which was directed, x of gamma is the set of all possible orientations, directions on the edges of the graph. Pardon?
You must have a linear space.
No, I don't need a linear space.
The element vector number is orientation such as that. Is that right? And then you're saying one set of orientation is these included some other. Give an example.
Yes, I gave an example. What did you say? Yeah, it is a function of the edges which chooses orientations. Yeah. The second operation takes an orientation on the edge, and it's a pair, an edge with the choice of orientation. So it's a function. Edge. Sorry.
Do we understand it correctly that it's just a rotation around the function?
So this is this is an element, edge and direction. Yeah, it's a function, so it's this way. X of gamma is a set of maps from the edges of the graph to Z2. Yeah, the set of directions. So, that's right. So it's two element set of directions. Directions on the edges. On the edge. So sigma 1 changes this choice of orientation. Sigma 1 changes the choice of orientation of an edge. Yeah. Of all edges simultaneously. Yeah. What? The orbits. Wait. No, it's important to have those orientations here because I want to construct a compact Riemann surface, and that's important to have. And there, it's important to have orientations. So, yeah. The red definition.
Is section gamma?
Yes. So. And sigma 0 is defined as the next edge of this. Yeah, but I want to have the edge of this sigma 0. I want to have this the beginning of it. I want to have the beginning of it as the. Oh, I see. Yeah. Okay. I think this is right. So it's not all possible directions.
Can we say that an element of X gamma is an edge together with an orientation? No? It's not that?
No.
Okay.
The set of oriented edges. You convinced me. I'm sorry, I'm not really a specialist in this field.
Why wouldn't you just tell what you want? I mean, what's the final purpose?
So the answer was yes.
The final purpose is on a graph with a choice of directions, I want to construct a Riemann surface. That's the final purpose. And I think I know how to do this. Now, well, this Riemann surface was an oriented surface. It wasn't, it wasn't really a unique. I wasn't constructing uniquely a Riemann surface, even if the graph was matrixed. No, it was a class of Riemann surfaces that we construct because I didn't tell. That's right, but I want to construct a compact Riemann surface, and that's a slight difference. Yeah, infinite. Yeah, this is what I wanted to do, but okay. Yeah, so all right. So yeah, now let's. I think x of gamma should be the set of oriented edges now, and then we take sigma 1, which changes the edge, the directions of all edges, and indeed the orbits of sigma 1 in this case will be the edges of gamma. All right, and then sigma naught will take you to the next edge yeah, actually this is right. Yeah, so we'll take it to the next edge in the cyclic order. Now sigma 1, sigma naught to the next oriented edge in the cyclic order. Now sigma 1, sigma naught, and this picture is correct. E is the old thing, and the white things are. Oh, yeah. Then this picture should be like that. Okay, and now from this one you would get the white. So if this was E1, then which is the same as that one, then this will be sigma naught E1. So here's the picture. Now the situation is that if you take sigma 1, sigma naught, and take its orbits, then this will be exactly the cycles, the boundary cycles of the graph. Just call those guys the boundary cycles. Obviously, they correspond to those boundary components that we obtained by doing this oriented Riemann surface. Now I will construct the. So, well, just visualize this picture over here about what's going on. Now I want to construct an oriented Riemann surface out of a compact Riemann surface out of this picture. So C gamma M will now be obtained as follows. Well, let's take the simplex. Let's take with each edge. Let's take edge cross the R plus, where R plus is the semi-integral. and take the standard metric on R plus, and say the standard Euclidean metric on R plus, and on E we have this metric because E is an interval of the line of length L1, of length of a certain length L. So remember that this is a metrized graph. So here we have just take the Euclidean metric, and then what we'll get is I want to also take a one-point compactification of this. So I will take this guy and a one-point compactification. What is this? This is an edge. You have an edge E, and then you take the edge cross R plus, and then you compactify all points at infinity by 1 point. So this will become, well, after all, this will become a simplex with a certain rather strange metric on it. So this is just a 2 simplex with a metric imposed on it. Now I want to glue things together, and so I take those simplices and mod it out by, and I make some identifications. Now the identifications I've got to make are the following. You take, first of all, you identify E cross 0 with, you glue E cross 0 with sigma 1E cross 0. This means the following, that if you have an edge, an oriented edge, and you sort of put the simplex on your left, then for sigma E, you revert the orientation of this, and therefore you put your simplex again on the left of your oriented edge. And this gives you this picture with 2 simplices identified at the base. Now the next step is to make an identification here. So what was the formula that I was using? Oh, okay. So the other identification will be you identify the terminal this is called sigma infinity, the composition of sigma 1 and sigma naught. So you take the terminal vertex of the edge sigma infinity E and identify this cross R with the initial edge of E cross R. So this does the following. Now let's see what it does. If you had another edge coming out of this picture, and we constructed, well, maybe I should take say yellow chalk. So that's another edge, E prime. What we do there, on each edge we construct this triangle on each oriented edge, and then we and then we identify. So this was this identification only. Now that we identify the following: the terminal vertex of sigma infinity is the following. E is going from here to here. So this gives us, well, let me put a prime, let me direct it this way, because I want to glue this edge with this edge. So E, I'm taking this triangle, this simplex on E oriented this way. I've taken this simplex on E prime oriented this way, and what is sigma infinity of E? We take E, we flip it over here, and then this is the next edge in here in the set of oriented edge well, it should be the set of possible orientations, in fact. Then we change this, apply sigma naught, sorry, apply sigma 1, which changes the orientation. And so so the first sigma naught thing gives us this, and then sigma 1 applied to that changes this orientation. So it will be this particular edge, which I have over here, and I identify the terminal point vertex of this edge cross R, so I identify this guy with this guy, which is the initial vertex of this times R. So I glue those things together. And this gives me a certain oriented Riemann surface. When I perform all of these gluings, it gives me a certain oriented Riemann surface with punctures and with a metric, with the Riemannian metric on it. So that these points will be infinitely far away in this metric. Now, yeah, except that it will be. You don't get a Riemannian metric at this vertices, of course. Yeah, you get a metric in which those vertices will be infinitely far away. That's right. Yeah, the angle will be bigger than 2 pi. Metric will be indeed bigger than 2 pi. So I don't know what to do. It still defines the Riemann surface structure, of course. Yeah, it's, what's wrong with that? Okay. Well, it's still a metric. It's still a metric on the surface, right? And so after this. To see? Okay, so after this process is completed, we get a Riemann surface C of gamma m. Let me switch to white chart again. C of gamma m with C of gamma m with some deleted point or marked punctures with some punctures, which are those points of infinity. That is, points at infinity in this metric. Okay. Now, there is this theorem of Strebel that allows you, well, maybe first of all, let me put this theorem of Strebel as a proof of the theorem that I wanted to be the climax of the talk, which is RGN, a set of metrized graphs, on which you can introduce the topology, which is this natural topology that, if you consider all possible sets as isometry classes of metrized Riemann graphs of this kind, then you can identify, introduce a topology on them, say, if the number of edges is fixed and the topological type of the edge of the graph is fixed, the combinatorial type of the graph is fixed, then you can introduce topology just by identifying it with the product of R pluses. Now, if you consider the set if you consider different graphs, then you can identify different graphs, again going like in the complex, in the graph complex, if the length of one of the edges goes to 0, then you identify it with the graph, with the metrized graph on which this edge is contracted. So you construct this topological space, and then the theorem is that the space is homeomorphic. So is homeomorphic to the modular space MGN of complex Riemann surfaces of genus G with n punctures. So these are complex, in the modular space, complex Riemann surfaces with n punctures and having genus G. Cross R to the power n, and then divided by the action of the symmetric group which commutes the punctures. This is a theorem attributed to Bob Penner. And the second theorem in this context is the theorem of Kontsevich, which identifies the graph complex, G, the homology of the graph complex, GN dot, rational, actually it should be the rational homology, with the homology of the modular space. So MGN. Here I would put a plus here, and r greater than 0, and MGN over Sn. So, let's see, for what time do they start? Oh, minus 2 minutes? Okay. So, well, maybe I write down this, what this story is based on, and on RGM, the topology is given by the...
Isn't the second statement a corollary of the first?
The structure... Alright, so this is all based on the following theorem, which I heard, the theorem of Strevel, which says the following, which is the following statement, that which actually makes this identification, the way I word this, it will really make this identification between Riemann surfaces and graphs, and Riemann surfaces constructed from graphs, to be pretty obvious. So let Cx1 through xn be a connected Riemann surface, with n punctures, such that its Euler characteristic, if you remove those surfaces, is negative. And also, let's have numbers C1 through Cn, which are greater than 0. Then there is an endpoint, is the statement is then there's just some numbers, just some real numbers which are pointed 0. Then there is an endpoint is, so an endpoint is metrized ribbon graph gamma n with cycles of circumference CI such that the Riemann surface, this Riemann surface C of gamma m is isomorphic to Cx1 through xn. And moreover, this metrized graph is unique. So, moreover, it's unique. Moreover, this gamma m is unique up to an isometry. So, if we believe in this theorem, then this homeomorphism is practically just a restatement of this theorem. So, then the way to prove Koncevich's theorem is to consider a certain the spectral, the filtration, first of all, which corresponds to the topological types of graphs of ribbon graphs. We will have to look at this RGM of metrized ribbon graphs. And then the statement is that this spectral sequence collapses in the first term, and this gives you exactly the graph complex, and therefore the homology, we have this identification with the homology of the modular space. Yeah. Well, the axisymmetric group comes from the following fact, that you don't really have an identification, a labeling or an ordering on the holes. You just obtain those holes if you construct a Riemann surface from a graph. You don't have, you don't know which hole is number 1, which hole is number 2. You don't have an ordering term. The filtration is by the topological type of the graph. It's basically the is the filtration by the set of vertices of the graph. By the set of vertices. It's exactly this filtration that you see in the graph complex.
So Koncevich's result is that he collapses in E2 rationally, but maybe not.
Yeah, he always formulates his results over the rationals. Just to be on the safe side. So I don't know about non-rational. Actually, I think it's much harder to do it non-rationally because of the issues. I can see where number 2 shows up in the picture, and this is related to the tadpoles, to the little loops. So I guess this is it. There is also a wonderful construction which allows you to construct from a certain infinity, well, from actually an arbitrary infinity algebra. It allows you to construct a finite dimensional infinity algebra with an invariant scalar product in the standard sense, not in the sense that Thomas Tadler was describing. It allows you to construct a cohomology class on the basically on this space RGN, and also there is a statement by Koncevich that this way from certain specific A-infinity algebras you will be getting the tautological classes of the modular space, which is some important part of the modular spaces. And these are actually obtained from one-dimensional A-infinity algebras, very simple one-dimensional A-infinity algebras. And those are really beautiful constructions which you start with some state model on the ribbon graph. You attach to given an infinity algebra, you attach the structure constants at the vertices of the ribbon graph, and you make a partition function, and this gives you a sort of number out of the graph, and this way you get a class. Well, if you have numbers on the graph, then you can have a cohomology classes in terms of graph cohomology, which means that you would be dealing with cohomology classes on the modular spaces, and actually the infinity condition tells you that it should be a co-cycle. So it is all very relevant to this conference, all very physical. And as I told you, I'm not a specialist in this area. I have my field is quite different. You know what my field is?
Question, please.
This theorem that could be the same as pure
Louder?
No.
Doesn't this, it's just a bibliographic question, doesn't this theorem contribute to savage actually appear in Penner's 86?
Well, let's ask Penner. I thought, is he around?
Doesn't he construct a isomorphism?
But I'd like to make a comment. Here you see kind of three theorems that are closely related. This is by an analyst. Straight away, like those percentages. Penner's viewpoint was to try to construct a Selby composition.
Right.
If you take his picture, this actual theorem, you say which is obvious, there's nothing to prove because it's a Selby composition. However, David's viewpoint is to make it more algebraic. You just don't need cells and all this. It's a really combinatorial construction of graphs with many related constructions, which David uses to solve many related problems. So in fact, you shouldn't think of these as, like you sort of said, this theorem makes that obvious, that theorem makes this obvious.
Yeah, that's
it's sort
true.
of like they're different points of view. Here's
Is there-
an analyst,
okay.
here's a cell complex guy, here's an algebraist. So it's like three fields. But the results are obvious. If you know any of these things, these three things are obvious. The point of view is wonderful because they just all like parents explaining this wonderful thing. Three different graph complexes solve three different problems. So it's not like this theorem. There's points of view.
So actually, as it is for the calendar, I find the thing most confusing because on the left is very different options. One side of the you're trying to find the connection between these logic. Which two are the G, and the homology.
If you have a space, it's exactly like a topology. You start with a space, you divide it into cells. You take the cells out, you put a label on it called algebra. You take a chain complex, you write a boundary operator. See, the boundaries of these Penner cells are exactly the base operators of the Sandwich space. So it's the process of algebraic topology. So if you just, because David is pointing out that you can just say the cell complex without saying it's a cell complex. Just give the chain complex.
So it should be like to give you a symmetrical position.
But there's a division. There's a symmetric group there in the fixed points. So you have to, worry about it. You say rationals. I think it's really these points of view. There's this thing that things go towards the algebra. He had to play some part in the analysis. Penner had to sort of understand the analysis and use it to get it down to the cell complex. The same is extracting out of that. There's this algebra combinatorial.
This modular space you're talking about is not confusing. Because there's
No.
all those green cells.
No, that's because the loop, you add to the boundary operator the last three loops.
M bar is if you add
And there's another point. I don't think the H1 orientation is important because any automorphism with direct graph.
oh, it wasn't important at this moment, but it was later on in the complex. It's not important for here. You don't fix for graphs here. You don't fix any orientation on H1. the orientation, as far as I understand, shows up in when you pass to the homology of this.
Because any automorphism of the graph preserves the orientation of the edges. Any orientation of the graph is going to see the order of the homomorphism of the surface. So the reflective transformation of H1 preserves orientation.
Yes, that's right.
So the orientation of H1 is a bit more.
Okay. Well, somehow.
Last thing is the orientation.
Okay.
Okay, any more questions? Comments? Madam?